Hello, everyone. I'm very happy to be here today to talk about research we've been doing in Saarland University. It's joint work with people from the Compiler Design Lab in Saarland University. So I just wanted to start this presentation with a few words about me, so that you know what I'm basically coming from. I'm a PhD student doing research mostly on language support for high-performance rendering. And all the work I've done is work we've been doing both in the computer graphics lab and the compiler design lab, so it's a close collaboration to design tools that are better suited for both graphics and offer really good compiler technology. So I'll start the presentation with a traditional trade-off that you've probably seen somewhere else. The idea here is that what we want is to write portable, straightforward code and obtain good performance. But in practice, what we have is something completely different. It's either you write straightforward code or textbook code, and then you get poor performance, or you have to write really non-portable and complex, intricate algorithms to end up with good performance. So it's not what we would like to have, and clearly there's work to do on the compiler side to improve these things. So in particular in graphics, if you want to write a path tracer, there is an example here. It's the path tracer we write for the realistic image synthesis course, which we do in Saarland University. It's a small path tracer with multiple importance sampling. It's for the students to learn how to write the path tracer, and it's written in C++, and still we do some algorithmic optimizations like building BVHs using the surface area heuristic to have a good acceleration data structure. We also use optimized ray traversal, even though it's not vectorized or anything. And we use OpenMP to parallelize things. So then what we do is we just tell the compiler, well, please optimize this path tracer we've just wrote, and use the native architecture and use OpenMP. So that's all we do. And then we hope for the best. If you take a scene like that, it's a pretty simple scene. It has 500,000 triangles, a couple of thousands of lights and materials. It's not really like a complex scene, but it's good enough to measure the performance of that path tracer. And this is what you end up with. So you end up with 62% of the time spent just doing ray traversal. So finding intersection between a ray and the geometry in the scene. 12% of the time is spent in the render loop, which is just some sort of glue code which connects the traversal and the material system. Then you have 9% of the time spent in the material system, which is the lies, the materials sampling, evaluating the BRDFs. And finally, 8% of the time is spent doing math, and by that I mean calling the power function or the sine function or cosine function. So clearly we could do better here, because 62% is a bit a large proportion of the time. And so the focus of the talk will then be on optimizing this particular piece of code that's responsible for finding intersections between the scene and array. And so if you want to optimize this piece of code, which we call BVH traversal, what we do is typically we start with algorithmic optimizations. And these are in particular in this context to have a good traversal order so that you don't traverse too many nodes in the tree. You also want to simplify your array box intersections as much as you can. And you also want to pre-compute as much as possible for your intersection routines. So all these things have actually been applied in this renderer that we have for the course. So it's still not enough, and you want to do more than this. So what you will end up doing is something more hardware tailored. You would apply vectorization, for instance, and then you have to know what type of instruction set you have. You can use, for instance, SSE, which is available pretty much everywhere, or you could use AVX or AVX2 even. You can also inline your array box and array triangle tests, which will hopefully speed up things, because you can then use your registers in a better way, and you have no overhead in the function calls anymore. You can use also wider bounding volume hierarchies, which will allow you to vectorize for single rays. And you can also use fuse multiply adds whenever it's possible, if you have the instruction set for that. The problem with this is that these optimizations, they depend on the use case. And typically, for instance, a specific type of vectorization, like packet tracing, which is tracing packets of rays and intersecting them with your tree, is only worth it if your rays are coherent. And if you vectorize your traversal with one ray and then multiple primitives, then you end up having something that works for incoherent rays, but that's not really as good as packet traversal for coherent rays. So you need to be able to specialize your code to do that. So to sum things up, what you need is compilers that allow you to do low-level optimizations, like vectorization, parization, or inlining, in a really controlled manner. And you also want to let the programmer express generic concepts so that he writes the code only once, and then specialize it for a given use case to get the best performance without having to write it a second time. So far, I've only talked about the concepts, and I want to see if, for instance, C++ fits the bill, in particular in the context of all these points I've mentioned before. In C++, if you write a power function, it's a nice example because it's rather small and understandable. So this is a power function. It just computes x to the power of n, and it does so with a fast exponentiation algorithm. And so it could be that because you know the exponent, you want to generate the exact sequence of multiplications for the power function. And it would be nice if you could just take this function and say, then I know n, then give me the sequence of multiplications for x, even if you don't know x. So now a naive approach would be to say, okay, I could always inline the function. If I always inline the function, then I will end up with having the exact sequence of calls I want. The problem here is the only annotations that you can tell your compiler is to always inline regardless of whether or not you know your exponent. That obviously won't work because the compiler cannot do this in the case where the exponent is not known. So if you even in C++ 14, you can also use the generalized constexpr, which is basically saying that you can completely evaluate this function, and it works well in the case where you know both the exponent and the value to exponentiate, but that doesn't work if you only know the exponent and not x. So what you end up doing in C++ is something like this. You create a data structure called power, and then you use template specialization to do that. And so with the base case being 0, you just return the value 1, which is at the bottom. And at the top, you have the general case, which is the recursive case when the exponent is not 0. And so here it works. It works, but if you had written this algorithm, instead of using a recursive function, using imperative style, an imperative style while loop, for instance, you would not be able to do this transformation as easily. And besides, you just ended up writing the same code twice, once for the case where you don't know the exponent and once for the case where you know the exponent. So it's not the optimal solution here. Now the second thing I wanted to talk about is vectorization. Vectorization is important, and here it's a large piece of code. You don't have to really care about what it's doing. All you have to know is like this Muller-Trumbull ray triangle intersection test. It takes a ray, a triangle, and it computes the intersection between the two. It does so by looking at the barycentric coordinates on the triangle and then figuring out whether or not the intersection point lies within the triangle. And then you compare the time of intersection with the given range that's allowed on your array. That's all it does. So it's a bit of math and two conditions, basically. If you want to vectorize this piece of code, if you take the intersection routine from memory, which has been written by Intel engineers, it's the one here. It's basically taking one ray and then intersecting it with several primitives here, several triangles. And so it looks pretty similar to what you've seen before, except now you have different data types for vectors. And Embry uses operator overloading and custom classes to hide so that you don't have to write intrinsics directly, which is pretty nice, because here, as you can see, there is no architecture-specific code. And then you end up with having vectorization for your single array case. Now, in the packet traversal case, you have multiple arrays with one primitive, and therefore you have to write a different version of that function. And what you have in Embry is this, which is a different version of the same function. It's slightly different. It takes, in this case, multiple arrays and does pretty much the same thing with a few differences here and there, but it's basically the same algorithm, except that now the vectorization scheme is different. So there is code duplication to be able to write these intersection routines. So why is automatic vectorization difficult? So why can't we just write this scalar version of the function and automatically get the best performance? After all, it should be possible. And the reason is that the compiler has to first off determine whether this transformation is legal, whether you can actually transform your scalar function into a vectorized function. So it's really difficult because there are many problems on the way. You need to figure out, for instance, whether or not it will terminate, or whether or not the algorithm actually is amenable to vectorization in the first place. And most of these problems, if they're not NP-hard, they're actually undecidable. So that's the first problem. The second problem is you want to know whether or not you actually want to perform this transformation. Maybe it's not even worth it. Maybe if you take the intersection routine, vectorize it, you will end up with something slower. So this is also a difficult and tricky question to answer by a compiler, by a machine, because it has to have an accurate model of the machine. You have to know, well, this instruction, when vectorized, will be this number of times faster, and I have to know that this branch here will be taken that many times compared to this other here, and you have to make decisions according to that. So unless you have really, really precise information on the behavior of the function at runtime, it's really difficult to make an accurate guess here. And finally, you then have to analyze the program, figure out, well, actually this thing can stay uniform, and this thing here can be vectorized. So the last part here is actually doable. So there's actually a solution for this problem. And in fact, the real problem is more the first 2 points. The third point is pretty much a solved problem. And so what I want to say here is that clearly we could just solve the problem by saying the programmer has to determine the cost and the legality. And then this problem is pretty much solved. And that's what guided vectorization is all about. You just let the programmer decide on where, when, and how you want to vectorize, and you end up with a compiler that can do vectorization. And there are existing solutions for this. There is 2 of them, the one you probably know about, and another one you probably don't know about because it's no longer developed. But the general idea for both of these solutions is you have C++ or C code, and then you attach vector information to the types in your program. You say, this variable here is an integer, but it's a vector. And so this is the min function in ISPC. So here I'm a bit, probably is a bit of an exaggeration, but the point I want to make in this slide is just to say that you have to come up with different versions of that function. So in ISPC, if you want to write the min function, you have to say whether the arguments are varying or uniform. And by default, if you don't write anything, they are varying, meaning they become vectors. Now, it could happen that in your program, you want to use your min function in different contexts, the context where one argument is varying, the other is uniform, or the other way around, or both are uniform. And because of this, you will have to write your min function several times because, well, it's part of the type, so you need the different min function. So that's the problem with ASPC. Obviously, with this, it's still better than just C++ because you don't have to care about intrinsics and you don't have to care about the platform. So it's already way better, but it's still not completely solving the issue here. Now, the other approach, which is Sierra, can leverage C++ templates. It works in a similar way. You annotate your type by saying, my type is a vector of length L, and you say that with the CMD keyword. And then you say it's either varying or uniform using the varying keyword. And the argument of the varying keyword is an integer that says whether it's varying or uniform. If it's 0, it's uniform. If it's 1, it's varying. And with this thing, you can leverage C++ templates to to compute the return type or the uniformness, basically compute whether or not the result is uniform or varying depending on if the arguments are varying or uniform. And you do this by taking the max between x and y here. So x is the information whether A is varying or uniform, and y is information whether B is uniform. And if you take the max, then the result is uniform only if both the arguments are uniform, which is what you want. Now, the problem with this approach is it leads to really subtle errors. So as the example below shows, because the information is part of the type, when you have the code written below, you first create a variable res, which takes A, and then because of this, the type of res is the same type as A. So if A is uniform but B is varying, then you end up assigning something varying to something uniform, and there you have a problem. So it's really subtle, and then you will get compiler errors, and you don't really, it's not obvious how to fix them. Besides, you also have to use template programming, meaning you have to do this thinking process of figuring out, well, if I take this, if I make the argument uniform here and uniform there, I end up with something uniform as a result. You have to think about this as a programmer all the time, which is also not so nice. So what we really want to have is something like this. We want to write a loop, say from 0 to 8, and then we want to say, please vectorize this loop. And here, the compiler could determine everything for you. I mean, at least on paper, if you look at this slide, you could figure out by yourself what has to be uniform or varying. You just see that the angle comes from outside, then it must be uniform. And then if you take the sign of something uniform, it's also uniform. You see that J, which is basically the loop counter plus some constant, has to be varying because the loop counter is varying. You see that K is initially uniform, but then you have some control flow, and then K becomes control dependent on the condition that's varying, and therefore has to become varying. So what the compiler can do here is run an analysis and figure this out, just as I just did here orally. It can just run through this process in a mechanical way. So I hope that at this point I've sort of motivated the reason why we're developing in the compiler in the first place, why we want to do this. So we're developing a compiler which is dialect of Rust with type inference. It allows the programmer to use a functional and imperative programming style. And the syntax is just as what you have below, so it looks like C. It's not so different. You introduce constants with a keyword let, and then if you have something non-constant, you have to use the mutable keyword. And so internally, we're using some technologies. There is, for instance, the high-order IR we're using internally, which allows us to do some interesting optimizations. And then out of this, we generate LLVM IR, which we vectorize using the region vectorizer. And finally, LLVM generates the appropriate machine code. So it does the job of instruction selection, register location, and all this stuff. All these things are available on GitHub, so if you want to have a look at them, just feel free to do so. Now I want to go back to this power function. It's here written in Impala. It's pretty similar to C++. There's not much difference actually. And if you want to specialize it, all you have to do is to tell the compiler, please inline this function when you know n. You do this with what we call a filter, which is a condition that you just place before the declaration of your function, which says, if you know n here, please just inline the function. So what will happen is if you call the power function with n equals 3, then the compiler will just inline the function, look at the ifs, evaluate them, because it can do it since n is known, and you'll end up with either no recursive call or a recursive call of one of the two cases. And then, because then you know n divided by 2 and n minus 1, you can continue that process until you reach the base case. So it's extremely simple, and it has the advantage that you can use the code in two different contexts, the context where you know n and the context where you don't know n, which is not what templates allow you to do. Now, if you want to do vectorization with Impala, it's also pretty simple. You just say, please vectorize this loop, and Impala will basically transform it for you. It will extract a function from the loop body, and it will send it to the region vectorizer, which will then take care of generating the proper vector code. And the nice thing about this approach is that you can change things easily. Say you want to change the vector width, then you just change the number, the number of lanes in the call to vectorize. If you want to change the vectorization scheme, if you have initially many arrays and then one box, as the example at the top, you can change it to intersect instead of one array with many boxes, as the example below, and it just works. You don't have to change anything in your code. Now, you can also do parallelization. You just annotate your loop by saying it's now parallel, please execute this on several cores. And under the hood, we're using TBB, so Intel threading blocks to schedule iterations. We also allow people to write code on GPUs, FPGAs. To do this, we have other types of functions, so one for each device. For CUDA, we have a function called CUDA, OpenCL, a function called OpenCL. And then, again, the compiler extracts a region to vectorize, and transforms this into a kernel, and then executes this on the device. So that's all for the language. I want to go back to the use case for it, which was array traversal. And in this case, I want to implement, say, an efficient algorithm for array traversal, which is hybrid array traversal. So hybrid array traversal is based on two different sub-techniques, which are basically packet traversal and single array traversal. And the idea is to switch from packet traversal at the top of the bottom, at the top of the tree, and then switch to single array traversal when SIMD efficiency drops. So initially, you have lanes full of arrays, and then as you progress through the tree, some lanes will become inactive, and then you lose efficiency. And to sort of solve this problem, you switch to single array traversal once you reach some certain threshold. And then in this algorithm, you want to support different ISAs. You want to support SSE, AVX, AVX2, and you also want to support different algorithm parameters, so different BVH types, for instance. So you need specialization. So the interesting thing about this test case is that you want to have both good vectorization and good specialization, which is a perfect use case for our compiler. So we start with array packet. The array packet traversal is a speculative way of traversing your tree. You traverse a child if any array in the packet wants to go, wants to intersect the child, in fact. So because of this, as I said, it's more efficient for coherent packets, but more importantly, it's really similar to a binary tree search. You have a binary tree, you want to search, is this element in my tree? It's really similar to that. And so I'm going to continue the example and the demonstration with binary tree search because it's simpler and fits in the slide. So in the binary tree search, you just have a function which takes a stack, a tree, and an element to search. What you do is you push the root node of the tree on the stack, and then you have a loop. And the loop is testing while the stack is not empty, and while not all layers have found the element in question. Then you pop a node, and then you check if the node is your element. If the node is your element, then you found, obviously, your element, so it's done. Otherwise, if the node is not a leaf, then you can test every child of the node. And if any lane desires to go through one part of the tree, then you will process it and push it on the stack. And so because of this, all the decisions are uniform, and your stack will remain uniform. And the any and all functions are provided by Impala, and they basically do this reduction on vector booleans. Now, at the call side, it looks like this. You just say, I have these elements, I have this tree, and I have this stack. Now I call my traversal function with a vector of size 4, and I end up with my vectorized binary search, and that's all. You don't need anything else. And so the analogy is that in binary trees traversal, the elements to find are basically the same as arrays for array packet traversal. And the tree in the binary tree traversal is just the BVH for array packet traversal. So that's the analogy here. Now I want to switch to the other part, which is single array traversal, which now uses vectorization in a slightly different way. Instead of having many arrays, you have one array, but you have multiple primitives. So what you do is you intersect this array with multiple primitives or multiple triangles, and because of this, there are two challenges here. You need to do reduction when you have multiple primitives to figure out which one is the closest, because in ray tracing you look at the scene, but you only look at the primitive that's closest to you, right? And you also need to do sorting for the traversal order. You want to go in the order so that you don't process nodes that are too far away. You want to process the nodes in the tree that are closer to your eye so that you find the intersection quicker. So to do the sorting, we use sorting networks. Sorting networks are basically sorting functions that will produce a fixed sequence of comparisons. For a given size, you end up with a fixed sequence of comparisons, and therefore you can make the network branchless, and you can sort your entire data in registers by loading everything, performing the compare and swap on the registers, and then storing back to memory. So it's interesting for this use case, and if you want to implement it in Impala, okay, you don't have to understand what's going on here, but it's pretty much like merge sort. You have two functions, one is called merge and the other is sort, and you have a number of elements, which is here in orange, and a comparison function, which does the job of comparing elements. All you have to do is to annotate your functions so that they become inlined when they terminate, which means when you know the range you're operating on in the sorting function. If you do this, then you can just call your sorting function with a fixed size and a comparison function, and the compiler will specialize your network for your number of elements and the comparison function without you doing anything, just annotating the functions. And so you will end up with the perfect sequence of instructions. Now for the second part that's required in single ray traversal, is vector reductions. So what we do is we use cyclic permutations. If you start with the following vector, which is 1573, what you can do is shift it by 2, and then use your reduction operator on the vector in the shifted value. What you'll end up is the vector at the bottom, which will compute the operator for consecutive elements, 2 consecutive elements. And then you do it a second time, but this time you shift by 1. And finally, you end up with the global reduction in every lane, like shown below. So here it's the minimum, and you get the minimum in every lane. If you want to implement this in Impala, it's pretty simple. You just write the following code above. You just say, if you know the length for which you're reducing, the vector length, then please inline. And the compiler will generate, again, the perfect sequence of shifts and calls to your operator without you doing anything. And finally, because the result is a vector, and the compiler cannot figure out that it's uniform before execution, you have to somehow tell the compiler still that it's uniform at this point. It's important because these are the parts that the compiler cannot determine. So they are actually a bit like the annotations in SPC, but only in the real case where the compiler cannot do this for you, which is this example. And so finally, the part of the traversal which combines the two ideas is hybrid traversal. And as I said, you start with packet tracing, and then you switch to single ray tracing when you don't have many active lanes. And the way you do this is something like this. You start by vectorizing for the packet. Then you have the traversal loop, which just pops nodes from the stack. Then you create a mask with the ballot intrinsic, which will give you a bit field telling for every bit whether the lane is active or not. So bit number 0, if it's 1, it says that lane number 0 is active. If it's 0, it's inactive. And if you do a pop count on this mask, you end up with the number of lanes that are active. And if it's below a certain threshold, you switch to single ray traversal, and for every bit set in this mask, which means every lane that's active, then you can run a single ray traversal. Otherwise, you just do the normal packet traversal. And that's all you need to do. So to wrap up, we have some high-level code, which gives us a description that's platform agnostic, and mostly, it's just an algorithmic description, really, of what you would do. And you use specialization, guided vectorization to come up with good code at the end. What's important here is that you just have a function, and you just write your arguments, and the designer of the function decides when and how to specialize. So if you didn't know about the implementation of the function here, you don't know what it does, but you know that you're going to get the best code possible with this combination of arguments, which is really nice. Now, to evaluate those kernels, we compare them with Embry because it's the state of the art in terms of performance. It's really fast. Here we decided to compile it with Clang because the backend is also LLVM for Clang, so we compare exactly the same type of code and we don't compare different compilers, so apples with oranges. And we use a Skylake i7 for comparison on a single core. With different types of rays that come from the path tracer, we end up with this type of results. The horizontal bar here is Embry. And what you can see here is that the single ray traversal is within 15 to 12% slower, and the hybrid traversal is between a bit faster and a bit slower, within 10% of Embry. So it's a pretty good result considering that Embry is written with low-level intrinsics under the hood, and it's highly optimized. So these kernels haven't been written over the course of several years; they've been written over the course of several weeks. So it's a really completely different scale. And to prove that the vectorization is also platform agnostic, we can run these kernels on a different platform. We can just take them and just vectorize them a bit differently. So in ARM, unfortunately, there is no instruction for the ballot intrinsic. So there's no way to perform this hybrid or single ray traversal, unfortunately. So we ended up just doing the packet traversal in that case, which ended up being almost twice as fast for coherent rays and as slow as the scalar version for incoherent rays. One thing is important here, so we're not comparing against Embry because Embry doesn't run on ARM, but we are comparing it against the scalar version of the kernel, which is obtained just by taking the code and saying, I don't want to vectorize, in fact. I just want to get the code which is not vectorized. So you don't have to write a different version of the kernel. You just change the parameters again. So with this approach, we don't have to care too much about vectorization itself, and the compiler will select the proper instruction set whenever it's available. But still, you have to be aware of the fact that on some systems, you might not have the proper instruction to run your algorithm in an efficient manner. As a conclusion to this talk, I would like to say that I hope that this was the proof that you could write high-performance kernels using high-level code, which is close to what you would have written in C++, just in a different language and slightly different technology, but it's pretty similar. And the tools here are specialization and guided vectorization, which are important and allow you to make the code generic enough. The performance gap we have with the LLVM-based compiled version of Embry is mostly due to the quality of the code that LLVM generates. We're working on that, so it will hopefully improve. Also, it depends on the quality of the backend, which is not really our responsibility because we don't directly work on LLVM. And so here it's mostly, over time, the quality of LLVM improving. Now, if you want to add these features in the mainstream language, and this is also the reason why we haven't done that ourselves, the reason is that you need a lot of work to be able to combine, for instance, C++ with such a feature in order not to break the entire compiler and not to break anything here. So, because we're only a small team, we design our own language and actually end up being easier than to use something that already exists. Now, if you're interested to work on this or something more in computer graphics, we also have open positions at Saarland University, so if you're interested, just contact me after the talk.